Thank you. Yes, thank you for being here. I'm super excited to talk about the impact of memory allocation on performance. While working on CodeSpeed, we saw multiple strange things happen because of memory allocators. So I'm really excited to talk about that and demystify some stuff hidden behind that. So a little bit about myself first. Thank you. I'm French. Happy with that I'm not the only French speaker here. I'm a software engineer. You can follow me maybe on Twitter and GitHub. I worked on AI on embedded system and as well web development from like 10 years ago. And I got into Rust, the EuroRust ecosystem 2 years ago with the advent of code. So if you're wondering, I'm not really familiar with Rust or any new language. Honestly, I can only recommend the advent of code. It's really good. And this is mostly why I got really hooked into Rust. And as well, I'm maintaining and I built NoRM for Python and for MongoDB especially. And right now, it doesn't have yet a Rust core, but this is something that is a work in progress because it will bring some big performance improvement. So this is the project, the open source project I'm working actively on those days. And since 2 years now, I'm building actively CodeSpeed, and we are as well happy to sponsor the conference. So just for a quick idea on CodeSpeed, because we'll talk about performance and measuring performance quite a lot later on during this talk. The core idea of CodeSpeed is to have consistent performance measurement, because measuring performance accurately is extremely complicated in noisy environments, and to have it integrated in existing benchmarking libraries like Criterion or Python benchmark in Python, for example, and to have it run on virtual machines, even on GitHub runners that can be extremely noisy. And as well, we bring performance reports directly into pull requests. Okay, there's a bit of delay. Directly into pull requests as comments, so you can know when you're introducing a performance regression and know before you actually ship your code. And we are happy to be used by some popular open source project built in Rust, and there have been some supporters since the beginning of working on CodeSpeed, so we are super excited that they use the tool and they get good value out of it. So back to the talk. Why do we need to allocate memory again? So because actually it's not always required to allocate memory, and we could often end up by just allocating memory ourselves and creating some kind of dummy allocators. So for example, if we take this piece of code, it's basically just a program that will take as an input your address and give it back to you once you entered it. And so to do that, we simply allocate a memory pool, here like 32 bytes of a static buffer. And then when you're actually entering your address, we'll just copy each character you entered, and then we store it into our mutable buffer. So it works well when people are doing things that are expected, like in this example. Everything works perfectly. But when you get with bigger addresses, so basically when here our buffer is 32 byte long, it doesn't work as well. So for example, this is the address of the conference, and it's 32 characters, and so it overflows the buffer. So this is mostly why we need to have memory allocation. Before talking about memory allocation, a quick recap and a heads up on the different type of memory you can have. So basically, usually we will separate it into static memory, heap memory, and stack memory. So in Rust, static memory, you will allocate it using the static keyword. And like this, for example, to allocate a static unsigned integer of 64-bit. And those variables are allocated at compile time, which means you need to know the size they will have during compilation, and you cannot really extend them during the runtime. So the keywords are static and static mut. When it's mutable, it's unsafe because it can lead to race conditions. If you have multiple threads, for example, accessing the same static variable, it's not really safe, and then you should kind of avoid using that. And this is as well why the static lifetime is the longest of all lifetime you can have in Rust for the variables, because actually the variable exists during the whole execution of the program. Just a side note, const are different from statics because often const will be, and I mean not often but always, they will be inline and don't really exist in memory. They don't have an address in memory. It's just at compile time they are replaced where they are used. And this static memory has an amazing performance because it's allocated at compile time, which means when you're using it during the runtime, there is nothing to do, nothing to allocate, nothing to free. Everything is there already, and your memory is already available. However, it brings really a limited flexibility and can lead to data races, especially when you're dealing with mutable static variables. The next kind of memory is a stack memory. This is probably a memory you need to use, and if you wrote a piece of Rust code, you used it. The idea is that it's kind of allocated at compile time and exists and is allocated with the same size during the execution. So for example, in Rust, you will allocate that with let and letmut, and they will be allocated on the stack when you enter a new scope, enter a new function, or when you exit this function, they will be deallocated. As well, for function arguments, depending on their size and the number, they might be allocated on the stack. So this is great for memory access performance as well, because all your closed data is stored together in memory. For example, if you have a function calling another function and you are accessing variables across those scopes, it will work very well because just one memory access will get you all the variables at once. So basically, instead of just reading small chunks of memory, when you're accessing memory, it's read by pages, and so a part of this memory will be loaded even if you don't really need to use it, which means you need less memory access to access your variables. And as well, when you allocate this stack memory, it's pretty simple because you just need to bump the stack pointer, and then you have your memory. One problem is you need to know the size at compile time, and as well, the stack cannot grow indefinitely, and it has a limited size. So here I have an example of a program that actually tells you about the size of your stack. So it's just using a system call. So basically, a system call is when instead of just executing your program, you're communicating with a kernel that is executing, that is basically the operating system. And so, for example, then we'll allocate a huge array of like 16 megabytes. And when we execute that, what happened is first it tells us about this max stack size and the current stack size, which is 8 megabytes. And then actually, when we try to allocate our array, it overflows, so it doesn't work. So we are limited by the stack in terms of quantity of data we can allocate. The last kind of memory, and this is really what is interesting for us today, is the heap memory. Often in Rust, you will use it by allocating strings, using box or vectors, and basically it's memory allocated at runtime by the allocator in Rust, and under the hood, the operating system, giving you more memory than what you initially had when you started running the program. Still, when we are using those kind of heap allocated variables, we still store a pointer to those variables on the stack. So it's not purely using just the heap to allocate memory, but as well just using some pointer memory chunks to store the variable on the stack. And this is extremely flexible. You can allocate virtually an unlimited size. You're just limited by the physical limit and physical constraint of your machine. But you can request any kind of amount of memory. And the allocation still needs bookkeeping and is costly. And this is about those costs that we're going to talk about today. So for a quick recap, static variables and static memory basically brings you memory with no overhead at runtime, but it's really limited at compile time. Stack variables give you a bit more flexibility, but still you cannot allocate dynamically sized variables. And they are still fast, so this is pretty interesting. And lastly, we have the heap memory, which is the slowest, and you need to allocate it during the runtime and ask and use an allocator to allocate on the heap. So to allocate on the heap, you need to have an allocator. And if you learned C, I'm sorry, I know this is a Rust conference and I'm showing a C snippet. Probably if you learned C at some point, you used malloc like this. And this is basically a memory allocator. And so this is probably the first use case of a memory allocator when you're learning programming. And actually, this malloc, free, calloc, and realloc are the kind of specification of what an allocator should be. So basically, malloc will ask and allocate a chunk of memory on the heap of size. Free will free this chunk of memory. calloc will allow you to allow multiple chunks of the same size. So if you want to alloc 10 chunks at once, this is really helpful. And realloc will allow you to resize some already allocated chunks of memory. So now a tricky question. If you think malloc is a system call, can you raise your hand? Okay. Okay, you're right. It's not a system call, but under the hood, it uses a few of them. Mostly, before it was BRK and SBRK to change the location of the program break and basically extend the process data segment. So this is a way to allocate memory dynamically at runtime, but it comes with a lot of limitation, especially around fragmentation, because you cannot really allocate separate chunks of memory. Now, the most common way to allocate memory is using the mmap system call, which creates a new mapping in the virtual address space. So I didn't really talk about it before, but basically, when you're executing your process, the kernel gives you a virtual address space, which means you're the only one to use your memory layout, and there are no other processes interacting in this memory space. And basically, what mmap does is give you a new window on the real memory into your virtual address space. And so now, for example, most common allocators like glibc malloc are using mmap exclusively if possible, and really not using BRK and SBRK anymore. So now to define a custom allocator in Rust, just a little lag. So to define an allocator in Rust, we cannot really use this malloc spec. What we'll use is, we have two possibilities, either to define a global allocator or to define some specific allocators that can be used on specific data structures. Okay, so the first way to implement an allocator is to use the global alloc trait. So this will define an allocator that will be used globally on your whole program. And so we need to implement two functions, alloc and dealloc. So it's exactly like malloc and free. One difference being that instead of just passing the size of memory we want, we can also specify the layout of this memory and give some more information about, for example, the alignment of the memory chunk we are requesting to the OS. Under the hood as well, we can implement some other methods that could be made faster, but they are also provided in the implementation of the trait. So it's not really needed to implement them except when we want really to optimize. But at first, if we want to implement a simple allocator, just implementing alloc and dealloc will be enough. And then to use this allocator, we use the attribute-like macro global allocator. So this is available since Rust 1.28 and end of 2018, basically. Before, it was not possible to define a custom allocator. But now you can, and you create, your allocator must be static, and you create it, and then it will be used by the process. And basically, as well, when this was introduced, so the possibility to select a custom allocator, the default allocator used in Rust by default changed from gmalloc to glibc malloc on Linux, on NX platforms, and heap alloc on Windows. And this gave really more flexibility to choosing the allocator when you're working with your programs. So if you want to implement, for example, a glibc malloc-based allocator, we can just implement this trait. So we create our structure that will represent our allocator, and then we just call malloc. So basically, malloc is available in the libc, so we can install the crate that will allow us to communicate with the libc from our Rust code. And then we need to do a little casting, because libc will return void type pointers, and in Rust, we don't really handle that. And I mean, the implementation, the trait definition doesn't want to have this kind of types. So we do some little casting. This is why this is not super nice to have a look at. And basically here we as well implement realloc, because it's provided by the libc spec and the glibc implementation. And essentially, this whole allocator is how the system allocator works in Rust now if you're working on Unix platforms, because by default it's using malloc. But there are some small details of implementation that are different. The other way to define an allocator is to use the allocator API. So this is newer and unstable, unfortunately. But the idea is that it really allows you to use an allocator for some specific data structures. So for example, if you're allocating a lot of vectors of small size, you can use a specific allocator for that. Or depending on the kind of data structure you're using, you can really select which kind of allocator you want to use. And so it comes with a few new APIs, for example, on vector, like new in, where you can select your allocator. With capacity in, you can get the allocator from a vector as well. And as well, you can move a vector from one allocator to another. And so this is the same thing. We have a trait. And here, the pointer is like the prototype is almost the same, except we use a bit smarter pointers here. And the allocate method is safe. And as well, here we use the input struct. So here, this struct is not implemented like this, but it's just to show you what it contains. Essentially, it contains the size of the memory you want to allocate, and as well the alignment, which will be helpful depending on the kind of memory you want to allocate. So the first allocator we can build using this API is a bump allocator. So essentially, a bump allocator is a kind of arena allocator. And an arena allocator is a kind of allocator where you allocate a chunk of memory, a big chunk of memory, and then you will do some sub-allocations in this allocator and this chunk of memory. So for example, if you want to allocate a small string, I will just allocate a huge chunk of memory, put your string first, and then bump my offset pointer in my allocator, and then store the variables like close to each other. So essentially, every time you allocate, you just have to bump a pointer, so it's close to how the memory is handled on the stack, except you manage almost everything. Also, a specificity of a bump allocator is that actually you don't deallocate the memory when something is called, like the drop method is called. You're not actually dropping any kind of memory, but when you drop the entire allocator, then you're freeing the memory, or you're just resetting the pointer, because you don't really care about what happened to that allocated memory. So this is extremely interesting, because it makes it really fast when you need to allocate and deallocate a lot of small objects, because you can just wipe them out all from the memory at once. So to implement this, the main idea is that we'll need to have 3 variables. The first one will be our chunk of memory. So here it's the pointer to a mutable U8. As well, we'll need the size of the arena, so in bytes. And lastly, we'll need the offset. And so we have an interior mutability here, because in the trait definition, we cannot mutate self directly. So basically, the offset will just store our pointer to the currently free data, and we'll just increase it over time. So the first method we need to implement is the allocation. So first we get the size and the align out of the layout that has been requested. Then we do a little arithmetic to make sure that our pointer is correctly aligned like our offset is correctly aligned with the requested alignment. Then we compute the new offset. So basically, when our memory will be allocated, our pointer will point toward our offset will be at a location where the memory is free after this location. So we compute this new location, and we make sure that actually it doesn't overflow the allocated arena, because otherwise we cannot allocate this memory. Then we get the actual pointer address from our offset, so the memory address. We do some little internal changing of variables, and then we cast it to a proper slice, and we return the pointer. When deallocating, so this is a simple constructor, like you just need to have a mutable pointer to an array of U8, and this will allow you to build the actual arena allocator. As well, we don't really see it here, but when we are deallocating, we are not doing anything, because the deallocation will happen only when the arena allocator is reset. The bump allocator is basically set into a new state from scratch. So to test it, we can write a simple algorithm. So basically here, I'm just allocating a static arena memory. So this memory is allocated at compile time. It's a static mut, so it's unsafe as well. And then I'm building the allocator out of these memory chunks that have been allocated statically. And then as well, I'm wrapping this into a verbose allocator. Then deallocating some stuff, and we can see here the result. And basically what's interesting to witness is actually when we are deallocating some memory, the arena allocator is not doing anything. So those two simple implementations will really help us to have some kind of baselines in the performance of those memory allocators. And some common challenges, if we don't just think about performance, for memory allocation can be the memory footprint, which relate quite closely to fragmentation. Basically, if you allocate a lot of chunk of memory and then you freeze them, you will end up allocating a lot of memory and requesting a lot of memory from the operating system, but the memory your program actually is using is really small, and so your program is not really memory efficient. And this is a big constraint from allocation, because you need to make something that can allocate fast, but as well, it needs to minimize fragmentation and the memory footprint. And the last constraint is predictability, because we can often involve random processes, and it means if you run a program once or twice, you won't have the same result, because the memory allocator might rearrange the memory using a background thread or some stuff like this. So having a predictable allocator is as well really interesting, especially when you want to measure the performance. So now about production-grade allocators. As I mentioned before having the possibility to specify a global allocator, a custom global allocator, Rust used gmalloc, really focusing on fragmentation avoidance, as I mentioned just before, so basically memory efficiency, and as well on scalable concurrency. So it was used by Rust before by default, and now by default we're using malloc from libc directly. Another popular allocator is memalloc from Microsoft. So the premise is pretty simple. memalloc is a compact general purpose allocator with excellent performance. So we'll verify that just later. And as well, as we talked about bump allocators, a good implementation is bump allows that allow you to spin bump allocators with memory allocated using the default allocator. So it's not static memory, as I showed with our simple allocator example. But this is a bump allocator, so it only removes and deallocates memory once you actually drop the allocator itself. So to measure allocation performance, here we'll use the CodeSpeed Wall-Time Runner. So basically it's a bare metal instance with 60-core ARM 64 CPU and 32 GB of RAM. The benchmarks are made with Criterion using the allocator API. So there will be a link to the source code at the end of the talk. And so the first benchmark we'll run is the benchmark written by glibc. So basically, to test their malloc implementation, they wrote a benchmark process. And so I re-implemented it in Rust. And the idea of this process is to allocate 1,600 chunks of chunk size bytes. So essentially, we allocate a lot of chunk of memory. Then we free half of those chunks in a first-in, first-out order. And then for the other half, we free the last one first and then the first ones. And so we'll measure that for various chunk size and see how multiple allocators perform on this benchmark. So here are the results. So here we are measuring time. So the less is the best, basically. So we can see first that our glibc malloc implementation is really close to the system allocator, so the default allocator you have when you're not specifying a custom allocator in Rust, which is reassuring because our implementation is not completely crazy and out of scope. So this is the first thing we can see. And as well, we can see that gmalloc, so the yellow one, is as well almost 3 times faster in this benchmark than the default allocator, which is super interesting because it means you can really get some performance improvement just by using gmalloc. But we can see as well that the green allocator, so memalloc, is even twice as fast as gmalloc, so it's even faster than it's like overall 10 times faster than the default allocator. And we can see that bump allo, so basically the orange allocator, the bump allocator, performs extremely well on small chunks. So when we allocate small chunks of 16 bytes to like 32 bytes, it's really even faster than memalloc. But when we actually scale to bigger chunk sizes, it gets really not that great because it needs to reallocate memory quite a lot. And since nothing is freed, it ends up using a lot of memory and doing a lot of allocations. But still, we can find out that when we are doing a lot of small allocations, using a bump allocator can be extremely fast and even faster than memalloc. So it's pretty interesting. So those benchmarks were single-threaded, so no concurrency, no anything parallelism, no parallelism. But here we will run this same benchmark, but using n thread running concurrently on the same allocator. So essentially, here we have a fixed chunk size to 128 bytes. And we'll do that with a few number of threads. And we can see that here, actually, gmalloc doesn't scale as well as the others. And by the way, there is no bump allo here because, unfortunately, even if it's very fast and very handy, it doesn't support in the default implementation. It's not thread safe, so you cannot use it cross-thread. But here we see that gmalloc, without fine-tuning or anything, out of the box, it doesn't perform as well as the other allocators. Then we have some other kind of benchmarks. Here we'll allocate a lot of memory and big chunks of memory. So basically, we'll repeat 1,000 times allocation of memory blocks with a random size from 5 to 25 megabytes. And we'll make sure that we only keep 20 of those chunks living in our allocator. So basically, if we are allocating a new chunk, we'll remove the other ones. And then, for this result, we can see that actually bump allo is still extremely fast. Our implementation using glibc malloc is a bit slower than the system allocator. And as well, we see that still gmalloc is performing very well and memalloc as well. Bump allo as well might be performing extremely well because it's allocating a lot of memory and not deallocating any chunk. And so here we don't have a memory footprint because this was not really the topic of the talk. But I guess that the actual memory requested to the OS might be completely increased compared to the other allocators. As a conclusion of those non-exhaustive benchmarks, and using bump allocators when dealing with a lot of short-lived small objects can be extremely handy in improving performance. So especially, for example, they are used in video game development when you're processing something to build a frame. You know that actually you will have to allocate a lot of objects, and at the end of this frame, you can wipe all those objects from the memory. And this is interesting because instead of deallocating every single small object, you can deallocate everything at once. And as well, use memalloc when the only constraint is performance and you don't really have time to fine-tune the parameters of the allocator, because out of the box, it's performing really, really better than the other allocators on most benchmarks. One drawback, though, is that memalloc, without any configuration, might create some non-deterministic measurements, and this might make your performance measurement and overall optimization attempt harder. And now, some small memory performance tricks. One is to try to use a stack instead of using the heap. So, for example, using small vecs. So here, for example, the idea behind the small vec is that it will be stored on the stack, and if it overflows a predefined length, so for example here 4, then it will be moved to the heap. So we try to minimize the allocation by allocating more space on the stack. And as well, another quick improvement we saw on many CodeSpace users is really to pre-allocate to avoid reallocs. So for example, if you're extending strings or vector, using with capacity will really lead to performance improvements. And for example, on OXC, it brings a 3% performance improvement just by using a with capacity kind of. So thank you, that's all. And yeah, if you have any questions, don't hesitate.